Assalamu alaikum. I hope you all are doing well. Today we're going to discuss an interesting topic. Today we'll be discussing cryptography, Caesar cipher, and one-time pad. Have you ever tried to send a secret key to someone special that can only be decrypted by that person using a special key? Well, people have been doing this since ancient time. This is called cryptography. Cryptography is the art of keeping information secret and safe by transforming it into a form that unintended recipients cannot understand. Cryptography is all about encryption and decryption. Converting our readable plain text to unreadable ciphertext is encryption, and decryption is vice versa. We add a key to the plain text to create ciphertext, and again, by reverting that key from the ciphertext, we get the plain text. It is believed that Julius Caesar used to communicate with his general using cryptography. Here, each letter is shifted 3 steps forward to encrypt. It's called Caesar cipher or shifted cipher. Let's see an example. Our plain text is stay positive. Here, S will become TUV, T will become UVW, A will become BCD, and Y will become ZAB. So in this way, with the help of this chart, we can convert the rest of the letters. And again, if we go backward 3 steps, we can decode it like VUTS, we get S. Again, for W, we can see that W represents T, and again you can see that D is actually A and B is actually Y. So in this way we can decode the rest of the letters too. Here's the code of shift cipher. We wrote a function to replace characters. It takes a character and a key as input. If the character is not a letter, then it will return it as it is. If it is a capital, it will set an offset of 65, otherwise 97, which is the ASCII value of capital A and small letter a respectively. Then we find the character code by removing the offset from the ASCII value of the character. We add the key with the character code to find the change. Then we divide it by 26, which is the number of alphabets in English, and set the remainder as the new character code. Then we add the offset to this code again and return it as a character. Then we take a plain text and a key to encode. If the key isn't numeric, we return an error message. Initially, the ciphertext is empty. We'll divide the key by 26 and keep the remainder as the key, because any multiple of 26 will make it loop around from A to Z, and the remainder is the final position. Then for each characters in plain text, we'll replace the character with the key using the function we discussed earlier. Finally, we'll print the ciphertext. Decoding is the same, except while replacing the characters, we'll use a negative key instead of a positive one. We designed a menu to operate our application, and then we tested it by encoding and decoding stay positive. It works fine. But there is a big problem. Here the number of possible combinations is the same as the number of alphabets. So in English, if we try all the 26 keys, one of them has to be the correct one for sure. And here we can see at 17 we get the message, kill the king tonight. So Caesar cipher is vulnerable to brute force attacks. Even without any key, one can decode it. So, and the solution to this is the one-time pad. In this cryptographic algorithm, a key contains letters whose corresponding values are used to encrypt the plain text. If the key is smaller than the plain text, then it will keep repeating. Here's an example. We can see meet me outside is being decoded by a B key. Here is the key. Here you can see that M, that is 12, and its counterpart on the key is B, that is 1. So 12 plus 1, that is 13, and the 13th letter in this chart right here is among this letter is N. In the same way, E is 4, and the counterpart of the key is D, that is 3. Total 3 plus 4, 7. So its ciphertext part will be H. So in the same way, we can encrypt the rest of the letters. Again, if we go backward, then we can decrypt the letters. Do you remember the formula? P equal to C minus K. Okay. To encrypt, we add the key to plain text, and to decrypt, we remove the key from the ciphertext. Okay. The best part of one-time pad is, unlike shift cipher, here there are unlimited possibilities and there is no way to verify which one is the correct plain text unless you know the right key. There can be multiple words which are valid within the number of letters in the plain text, but we can never know which one is the right unless we know the key. So here is the code for one-time pad with the same replace character functions here too. Here we have one more function to calculate the character norm of any key based on ASCII value, although this is kind of redundant. Then just like before, the ciphertext will be empty. We must count we're here looking at the encoding code. So just like before, the ciphertext will be empty. We must count the skips too, because if there is any space or punctuation, we have to make sure that those special characters do not affect our key and plain text matching. Then for each character in the plain text, we find the key by selecting the characters from the key based on the plain text character position minus number of skips and modulus length of the key. And if the plain text character is not an alphabet, we increase the number of skips. So in this way, we just keep replacing the characters, and once we're done, then we print the ciphertext. In the same way, we can decode the ciphertext, but when decoding, all we have to do is enter negative key. Here we have the minus in front of the minus before find keys function. So in this way we can decode it too. Then we have tested the program and we can see that it encrypts and decrypts correctly. Thus we can use the one-time pad to encrypt our data confidently. So thank you for watching. If you have any questions, you can let me know in the comment section. Thank you.